I occasionally get comments and personal messages from people who say that my work has helped inspire them to pursue an education in the natural sciences. These are by far my favorite type of messages to read. They're often accompanied by requests for advice on how to proceed, how to prepare, how to stay focused, motivated, and so on. I decided to make a video to try to cover all bases in a comprehensive and helpful fashion, so I'm going to tell you how to become a successful physics major and what you can expect if you choose to take this path. The first thing that I need to point out is that it doesn't matter how old, busy, or poor you are. If you want it badly enough, you can have it, provided that you work for it. One of my classmates is a fat 30-year-old who works 2 jobs, has kids, and still manages to attend every lecture and pass every exam. There is always a way to succeed if you're dedicated enough, and nobody will think any less of you if you choose to take a path that you might feel is undignified, like transferring to a university where every student is half your age after being stuck in a small-town community college for 7 years. There is no such thing as an undignified path to a physics degree, unless, of course, you got that degree from Bob Jones University. The second thing that you need to know is that you're going to need a lot of math, and I mean a lot of math. Trying to do physics without math is like trying to drive without gas in the tank. You're just not going to get very far. The good news is that with enough work and dedication, you can learn math regardless of how bad you are at it. I used to suck at math until I figured out how to learn it properly, how to study the right way, and get the most out of the time I spent trying to understand the material. In a moment, I'll dispense some of these tried and true methods. It used to be that I scraped by with C's in middle school algebra. Now I'm playing around with spherical harmonics and group theory. If you want it badly enough, you can have it, provided that you work for it. The next thing that I should tell you is that, as I think it goes without saying, learning physics isn't easy. There's a certain way to approach physics problems, a certain style of thinking that needs to be adopted. You see, doing physics is more than just deriving equations and accounting for variables. Doing physics is the art of problem solving. It's for this reason that physicists are so sought after in almost every industry. It's not that we're geniuses or anything, it's just that we know how to solve problems, which is a very rare skill that unfortunately cannot be taught in the classroom or read from a book. You can read a physics textbook until the cows come home. Hell, you can even go ahead and memorize every word in it, but you still won't learn how to do physics. Unfortunately, the only way to learn how to do physics is by doing physics. It's like learning to play the guitar. Reading instruction manuals and listening to other people play just isn't enough. If you want to learn how to play the guitar, you're going to have to pick up a guitar and start playing. When it comes to doing a physics problem, there are 2 main steps: setting up the necessary equations and solving them. Solving a physics equation is easy enough, but the part that won't come naturally to you is setting it up. I can confidently say that it's this aspect of physics that's the most difficult. Ask any physics major and they'll tell you. The hardest part about physics isn't the concepts. The hardest part isn't even the math. The hardest part of doing physics is turning a word problem into a math problem. Once you do that, the rest is what we sardonically like to call just math. It's hard to appreciate just how difficult and time-consuming physics can be until your feet are actually put to the fire. There is nothing that I can say that will adequately prepare you for the intensity of the subject's learning process, but with determination and perseverance, you can learn it. If you want it badly enough, you can have it, provided that you work for it. Finally, I should point out that the more you learn, the stupider you feel. It's a strange feeling, and it's not entirely bad, but the more you learn physics, the more you can appreciate just how vast and insurmountable the mountain of knowledge is. Some people are higher up on this mountain than others, but the higher you climb, the more of the mountain you see, and the more you come to understand the overwhelming futility of trying to climb to the top within one lifetime. Most of us look at men like Stephen Hawking as those who have reached the peak of this mountain, when in fact people like him have a better understanding than anyone else of how little one knows. First of all, you need to be fluent in algebra, geometry, and trigonometry. When doing calculations involving these maths, you shouldn't even hesitate. Some excellent resources for brushing up on and learning these topics cold are Khan Academy and Patrick JMT, which pump out amazingly concise videos that you can use in combination with any math textbook that hasn't been printed by Bob Jones University. In fact, Khan Academy and Patrick JMT are life-saving resources that can be used for everything that I'm about to say. I cannot tell you how many exams these men helped me pass as a result of their tutelage. Also very useful is Paul's online notes, which lay out all of the following branches of math in a very cohesive manner. After the basic math is learned, you need to learn single variable calculus. Learning how to take a derivative and how to integrate, what these mean physically as well as mathematically, and which situations are appropriate for implementing these methods, is essential to doing physics. Your understanding of physics will at best be superficial if you don't understand calculus. What's more, you need to know calculus cold. Taking a derivative should come as naturally to you as doing this. You should be able to do calculus in your sleep. At some point in your mathematical education, between learning how to integrate and how to solve partial differential equations, which comes much later, you'll need to learn sequences, series, and convergence tests, which all show up at some point or another in physics. Especially important is learning Taylor and Fourier series, as these are absolutely indispensable tools to have in your mathematical arsenal. After you learn how to differentiate and integrate single variables, you need to learn linear algebra. Linear algebra takes the ideas of high school algebra and generalizes them to as many spatial dimensions as one pleases. As far as mathematical concepts go, nothing in basic linear algebra is really all that new. It's merely a reformalization of algebraic concepts into a more useful form with new definitions and new operations that yield very useful results. There's usually no calculus involved unless you're taking a more advanced course in this topic, but that's unnecessary. After that, one usually learns differential equations, which is probably the most useful branch of math out there. First, you will learn ordinary differential equations, which involve concepts learned in single variable calculus, plus a little bit of linear algebra. Differential equations are extremely useful because they allow us to take complicated physical situations and formalize them in a way that can be analyzed. For example, let's look at a classical problem that shows up in the theory of differential equations. Suppose a 1,500-gallon tank initially contains 600 gallons of water with 5 pounds of salt dissolved in it. Water enters the tank at a rate of 9 gallons per hour, and the water entering the tank has a salt concentration that conforms to this function of time. If this liquid leaves the tank at a rate of 6 gallons per hour, how much salt is in the tank when it overflows? Without differential equations, you would have nowhere to even begin. It's a situation that's easy enough to imagine, but impossible to solve without advanced mathematical methods. After one learns ordinary differential equations, you'll have to learn partial differential equations, but first you'll need to learn multivariable calculus, which takes one-dimensional calculus and generalizes it to multiple dimensions. Once that's done, it's essential to not only learn basic methods of solving partial differential equations, like separation of variables and the method of characteristics, but more advanced methods like the power series method and integral transforms, especially Laplace and Fourier transformations. In general, though, when confronted with a partial differential equation in a physics problem, the separation of variables method is the physicist's first line of attack. It's at this point that you'll no longer be able to use Khan Academy, Patrick JMT, and Paul's online notes because they don't teach the more advanced mathematical methods that I'll be introducing now. Everything that I've described up to this point is what one might call baby maths. From this point forward, things began to get more serious, and I'd recommend using YouTube channels like MIT OpenCourseWare and Dr. Chris Tisdale to learn some of these subjects. One not so difficult but extremely powerful branch of math that I'd urge you to learn is complex variables, which includes complex analysis, conformal mapping, and integral transformations. The methods introduced in here are very good to learn and will be extremely useful in several branches of physics. Finally, the math that every physicist should know is calculus of variations, which involves functionals and isn't too difficult to figure out once you know the basics. Without calculus of variations, you cannot do advanced classical mechanics. From here on out, the type of physics you're interested in will determine the type of math that you should study. Do you like thermodynamics? Go learn information theory. Are you into fluid mechanics? Chaos theory is the way to go. Do you think that string theory is the shit? Go learn knot theory. If you're like me and are really into particle physics, group theory is absolutely indispensable. If you're also like me and think that general relativity is the coolest shit ever, then tensor calculus, differential geometry, and general topology are essential. There are many, many options in physics, and correspondingly, there are many, many routes that you can take in math. So now that we've talked about the mathematical journey, what about the physics journey? It's customary to begin by learning introductory classical mechanics, which includes kinematics, which is the study of how things move, and dynamics, which is the study of why things move. At this point, it's a good idea to at least have had some experience with calculus. Differential equations are likely to show up, especially when considering the harmonic oscillator and wave mechanics, but it's unlikely that you'll have to solve them at this stage of your education. After linear kinematics and dynamics are learned, angular kinematics and dynamics usually follow, followed by basic fluid mechanics and basic thermodynamics. Then, classical electromagnetism is taught, beginning with classical electrostatics and electrodynamics, followed by magnetism. It'll be at this point that multivariable calculus will become crucial. After magnetism is learned, the dynamics of electromagnetic waves will be introduced, followed by basic optics. After this point, one might learn special relativity. Once all of this is learned, you should also know the basics of partial differential equations and every math that preceded it. In other words, you should be done with the baby math. It generally takes about 2 years to get to this point. From here, the advanced physics courses will vary from university to university, but they will all include advanced mechanics, advanced electromagnetism, advanced thermodynamics, quantum mechanics, and any number of specialized courses like particle physics, cosmology, general relativity, condensed matter physics, advanced optics, nuclear physics, plasma physics, astrophysics, nonlinear phenomena, statistical mechanics, and so on. There are so many options to choose from that it would take me forever to list all of the topics associated with physics. I'm going to operate under the assumption that your physics education will be based on the standard lecture format. So, rule number 1, always attend lecture. This might seem obvious at first sight, but you'd be amazed at how many people skip out of the lectures because they think that they can cram all of the necessary information right before exams. And that usually doesn't work, so I'd recommend against it. Always go to lecture. And take good notes. This usually means copying whatever the lecturer writes on the board and listening to their explanations of what's going on. Rule number 2, skim the textbook just before class. You don't need to read the whole thing, but it's a good idea to read the relevant sections or chapters that will be covered in the lecture. In the beginning of the course, you'll usually be given a syllabus, which should assist you in deciding what to read before class. Rule number 3, take careful notes while reading the textbook. Reading through a math-oriented book is not like reading other types of books. Highlighting important passages and writing down important concepts isn't usually the best policy. What you should do is, pencil in hand, read through the text carefully and outline the logical and mathematical progression of ideas in each section. Important equations should be highlighted or boxed, and the derivations of these equations should not just be copied, but understood line by line. Learning how each step is related to the previous one is essential to understanding, rather than merely memorizing, a derivation. Some equations, like Schrödinger's equation or F equals ma, should be committed to memory. Others, like the adiabatic work expression, should be understood to the extent that you know how to use it and where it comes from, so that you'll be able to derive it should the situation call for you to do so. But generally, this is the sort of thing that you should refer to in your notes. Things like this shouldn't be memorized. As your experience with physics grows, you'll become better at distinguishing essential equations from non-essential ones. Rule number 4, do example problems. Typically, physics textbooks will give you example problems after covering a certain topic. The book will show you a situation and will show you how to set up a mathematical equation that models the physical situation, at which point you can go ahead and solve for whatever physical variable you're looking for. It's a good idea when solving physics problems to leave everything in variable form until the very end. It's easier to work with abstract mathematical expressions than it is to juggle a bunch of numbers and units around, and in any case, doing the former lets you see what's going on much more clearly and helps you understand how different physical variables relate. In addition to example problems, which hold your hand all the way through the solution, there are exercise problems, whose solutions you have to figure out on your own. These are the problems that show up in your homework or recommended exercise lists, and the most obvious policy for how to deal with these things is rule number 5. Don't leave homework to the last minute. Not because procrastination is a bad thing in and of itself, but because the last-minute rush will force you to try to get your work done before the deadline without having much regard for what you're learning. You'll be so desperate to get the work done on time that you'll end up missing out on the skills needed to actually work through and understand the physics, which is the whole point of the homework in the first place. Oftentimes, homework will contain a variety of problems as far as the difficulty level is concerned, so if you can, consult with your professor, teaching assistant, or an online resource to help you with the nastier exercises. Before you do any of that, though, you should probably consult with a classmate. I say a classmate, as in singular, because rule number 6, study in pairs. Research has consistently shown that when studying something, and this is especially true for physics and engineering, the ideal size of a study group is 2 people. Not 1, not 3, but 2. Trust me on this. If you want to get the most out of studying, do it in pairs. I cannot stress that enough. Rule number 7. Study for tests the right way. Usually the ideal time to start studying for a midterm or a final exam is a week and a half to 2 weeks prior to the test. Start earlier, and you run the risk of moving so slowly that you forget the things that you review in the beginning. And waiting until the weekend before is a very, 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 very bad idea. Usually. The right way to study for an exam is to reread the relevant parts of the book, going over your notes from the lecture and the book, and redoing all of the preceding homework. What's essential here is pacing yourself so that all of this is accomplished over the course of about 2 weeks. Oh, and don't forget to study in pairs. If you follow all of these rules to the letter, then I can guarantee at least an A- in any physics class that you take. Well, that's all I've got. I wish you the best in your academic pursuits, and I hope that you'll consider going to school and majoring in physics. It's a tough ride, but it's also quite rewarding. I'll leave some resources in the description box below for anyone who wants to get a personal taste of what a physics education will entail.